Hi everyone. This is day 2 Wireshark training. So these are the list of topics what we're going to discuss today. So let's start with layer 2. So we'll go with every layer. So layer 1 is it's all signals, and we have no control over layer 1. So Wireshark has no limitation with layer 1. So we have no access for layer 1. So the real picture comes from layer 2 from the Wireshark perspective, because your NIC that responds to layer 2. So let's look about what is layer 2 and what are the layer 2 headers. So let me open up my notepad. So before that, I want to just give you an overview about OESI reference model. Not too deep about that, but just want to give you a glimpse about OESI reference model. So let me open up my whiteboard, because we have to know where exactly this layer 2 fits in the OSI. So this is all these are the 7 layers of OSI. We all aware of it. This is application layer, presentation layer, and this is session layer, and this is transport layer, and this is network layer. Then comes data link layer, then the physical layer. So total 7 layers we got. And example, if this is your PC here, and this is connected, and this is your NIC card, network interface card, where it can be the communication can be a hardwired connection or a Wi-Fi connection. So the protocol used for hardwire is 802.3. We call this as a Ethernet hardwire connection, and the Wi-Fi, it is 802.11. So these are all the protocols. Then the 802.11 can be subdivided into 2 GHz band and 5 GHz band. This all decides about the speed of the your Wi-Fi. So the Wireshark doesn't have insight about something called as CRC errors. Frame check sequence. We call this as an FCS tag. So in the data link layer, what are the key things we should know about? So now we got it. So in the physical layer, I can now it is all about signals, and it can be a hardwired connection or it can be a Wi-Fi connection. And for the hardwired connection, I use 802.3. And for the wireless, I use 802.11. So when it comes to the data link layer, so what are the header types and what are the key values I should look into the data link layer? That's subjective. So now let's jump into the layer 2. So this is the layer 2 header here. If you look at this is a 14 bytes. So the Ethernet header is a 14 bytes value. This is something, it's been tucked, that's been appended along with your data payload. And this decides your MTU. So we discuss about that in the later class, but MTU is actually your total payload. That's called your maximum transmission unit. This is your actual payload. This is all appended. Always your destination MAC address comes. Then your source MAC address. So this is a 6-byte value, and this is a 6-byte value. And your ether type is a 2-byte. So what is the ether type? Ether type is something, okay, what is my next communication? It is ARP, right? This is an ether type example for ARP 0x0806. We can see this in Wireshark. But why ether type is so important? So what is my next communication? So if I am trying to ping, so what is the next protocol that comes in play? So that is ARP. So how the Wireshark will get to know about that? Okay, my next protocol is ARP, and by looking into the ether type, I'll get to know, okay, this is an ARP packet. So we'll discuss about what is other type of ether types we have. We have some other ether types like IPv4, IPv6. These are all the most commonly used ether types. So apart from that, this is your payload, and this last 4-byte is your checksum, your cyclic redundancy check, and you can see only in the interface status. The show interface status, we can say this is an interface statistics. We can see your CRC is increasing, then it is a problem with layer 1. It's a layer 1 issue. So the main header type we should focus on is the destination MAC, source MAC, and ether type. And the MTU, it cannot exceed 1500 bytes. Why is that? We'll check in the command prompt. For example, let me open up this. This MTU is going to be same for all the appliances. The MTU cannot exceed 1500. There is some exceptions for the Nexus switches where we send the jumbo frames. So your PC will actually do a fragmentation. So I'll come to that, but let me show you how to check your actual MTU. This is a command in Windows you can run. It's netstat interface IPv4 show subinterface will show you your MTU values here. This is going to be static. For PC, for all the the ports, switch ports, router ports. As I said, the exception is the Nexus switches where we can set your MTU. That is your jumbo frames. If I go to, this is a switch. And if I go back to any port here, if you try to set your MTU more than 1500, it doesn't support. So what if there is a Nexus switch in the middle, and what would be the scenario? If I got a Nexus switch, how this particular switch can handle the traffic? So now we got it where this layer 2 header comes in. So let me go into delete this. So if you look at your Nexus, maybe this is a 9-key switch, and you got your 2960 switch, a basic L2 switch. This particular interface, we are all talking about layer 2 header now. So if I set the MTU 1500 by default, this particular port, this is fast Ethernet 0/1. And if I set an MTU value something, this is fast Ethernet 0/2. And if I set an MTU value something like 9000 bytes, but the default value, the default MTU is 1500. And in the Nexus, if I try to set 9000 bytes, this particular box, my L2 switch, when it receives it, it's going to fragment the packet. So if you apply any QoS, if you apply your QoS, if you say do not fragment, your packet will be dropped. When you have your Nexus devices, you have to be cautious about this. So you should never set your do not fragment bit. And in some cases, there might be a production service where you set your higher MTU value. There is a chance of congestion. That's highly recommended. Do not set your do not fragment bits. So the packet should be fragmented only, then you can receive the higher MTU values. So it's always to have your packets to be fragmented. So from the switch perspective, how do I check? Is it my switch is fragmenting the packets and now I'm receiving all these jumbo frames? There is a command, show IP traffic, include. So there are 5 packets fragmented. Why? If I send here an example, this is a ping command where you can specify your MTU size. I'll tell you how we can do this in the lab. But if you see, this is actually the default value is 1500 bytes. But I have increased the fragment size here. So it is supposed to be 1500, but I'm dumping more packets here. So I see the fragmented packets here. So my PC is fragmenting. So one on the fly, it can just receive 1500 bytes from the source to destination. If I receive more than 1500 plus, so my box will be fragmenting the packets. So this all comes under layer 3. MTU, it's layer 2, and the fragmentation happens in layer 3. Your actual payload. So the key things we have to look at in the layer 2 headers, I'll give you a wrap up again. So we have to move more specific about destination MAC, source MAC, and ether type. And from the Wireshark perspective, it doesn't look about the CRC. So CRC, if you want to check your CRC, then you have to check your interface. Example, if I go show interface fast Ethernet 1/3, there you can see your CRC here. I don't see any CRC incrementing here, so my cabling is good. And apparently you will see the input errors. It happens parallelly with your CRC errors. So this can be also a cause of slowness, right? So from the layer 2 perspective, we are looking at the layer 2 is clean. There is no issues with layer 2. So the layer 2 communication, what are all the communication it happens in layer 2? And the layer 2, it can be a unicast, broadcast, and multicast. So now let's see how exactly the switch, since the switch is a layer 2 device, when it receives a multiple payload, example, if it receives a packet from, example, this is a destination, and this is my source. So when I receive a packet, and if there is something wrapped up inside the layer 2, like your packet address that is wrapped inside, this switch will be interested, and it is aware of only the MAC address, no other protocol it is aware of. So in the layer 2, it will check the source MAC, the destination MAC. That's it. The forwarding happens only between these two, destination MAC and source MAC. So apart from that, whatever the encapsulated packet it has, if it got for the upper layers, it's called a payload, and it's going to forward this packet back to layer 3. The same way, the layer 3 will wrap up the packet, and it will look for source IP and destination IP, and it will send this back to layer 4. So when a packet comes here, this particular unicast, broadcast, and multicast is all happening locally, not between the peer-to-peer. If you know about how the switch exactly works, example, if you connected multiple PCs like this, all it is aware of the local LAN. So this unicast, broadcast, and multicast happens within the local LAN. So how this particular switch will get to know about that? Example, if PC, this particular PC, it belongs to 10 network, and this belongs to 20 network. So what happens here, if these two networks are in a different network, and the objective of the switch is to find the destination MAC address. But since no traffic has been generated so far, I don't know anything about 20001, but how do I reach 20001? So here comes the role of ARP. Address Resolution Protocol. So what is the use of ARP? So why I'm talking about ARP in the layer 2? So to forward the MAC address, I definitely need the MAC address of the destination. So what are the packets I got here? So I got 10001. I got my layer 3 packet source, and my destination, I know about 20002. I want to reach this, but this PC is a layer 3 device. So I know about my source MAC address because the packet originates from my PC. So example, this is my MAC address, source MAC, but I don't know the destination MAC address. So now here comes the ARP. So what happens, this particular PC will send a ARP request. For the ARP request, who will send an ARP reply? That's the question. So since I don't know the destination MAC address, so the ARP has a mechanism to do a broadcast. It's a layer 2 broadcast. So when I do this from my layer 2 header, so it's going to put all F, means that it's going to broadcast the packet to all the port, right? It's like a flooding the packets out of all the connected ports. But since this 20001 is not in my network, so what it going to say, this particular PC, when it floods the packet, the particular gateway example here, it is 10002 that's configured for this particular network. Let's take this network as VLAN 10. And this particular port has been configured for VLAN 10 access port. So only one VLAN is allowed. So for this ARP request, this gateway is going to respond back and it's going to say, hey, you send it to me. This is my destination MAC address. I have this information in my routing table. You can forward the packet back to me and I'll do the forwarding because I am aware of that network. So once for this ARP request, actually it is supposed to be this PC to send the MAC address. But since I don't know, it is not in my local network. So the switch is a one local broadcast domain. So I don't know anything about, the network 20, and I don't know anything about the IP. So all I need is a MAC address to forward my frame. So it's going to put the IP address of this particular interface 10002 example, let it be CCC. So here for my ARP reply, I'll get a response for a destination MAC address as here CCC. And now I got all these details. I got source IP, I got source MAC address, I got destination IP, and I got destination MAC address. So now the packet will be forwarded back to the gateway of the router. So now again, the same process happens. It will go check inside the routing table and it know about the directly connected devices. I know about 20 network and as well as I know about 10 network. So what it's going to put? So it's going to put its own IP address as a source now. So now 20001. So one thing, your IP packet is never being changed. Only we are talking about ARP. Only the ARP IP details are changing here, not your actual IP headers. So now it's going to put 20001 as my source. And the destination is, example here, it's 3. So the destination is 20003. And again, I don't know the destination MAC address or all F. So now once this ARP request is received from all the broadcast domains, this particular PC will respond back saying, okay, this is my MAC address, DDD, and it got the destination MAC address now, and it's going to forward this packet back. So your IP header never changes. Only because of this ARP exchange, your packet is actually moving forward from one appliance to other appliances. This is how the packet forwarded. So this is called a broadcast. This is called layer 2 broadcast. So all F is a layer 2 broadcast. So let's talk about the unicast. Example, if there is a scenario where I got my switch and I got 3 PCs connected. So all the PCs are in same VLAN. So I got my gateway configured here as a VLAN 10. So in the layer 2 header, since I got my source MAC address now, we know about how flooding happens, and this particular switch maintains a TCAM table where you got all your MAC address saved. So now this is my source. So this is my source, and this is AAA, and this is VLAN 10. So this particular information, again, we call this as 802.1q protocol, where you're tagging your VLANs. We can see that in Wireshark how exactly we do the tagging and how we can see that inside the switch. So we tag this packet, so that's been appended back again into layer 2 header. So now I got destination MAC, source MAC, and along with my tagged value, 802.1q, and whatever the VLANs you are allowing, that will be tagged inside. And this is applicable only for trunk port. So this is called 802.1 tagging. All this information is inside the layer 2 header now. All this information is inside the layer 2. Now the packet forwarding happens between PC1 and PC2. I got few chats here, so I'll definitely, I'll give a time where we have a Q&A session. You can ask your questions for sure. So now if the PC1 and PC2, if it wants to communicate, and now my ARP request, since I don't want to go for my gateway because all in one broadcast domain. I don't need a gateway. Even if you are not assigning the gateway, the PCs can communicate each other. Why? Because it's going to send a broadcast back. Now for this ARP request, with all F, you will get an ARP reply back. This particular PC will send an ARP request. So it looks for this particular PC, that is 10.0.0.3 here. And this is 10.0.0.7. So this is my source IP. My destination IP is 10.0.0.3. An example here, my source MAC address is AA and destination MAC, I don't know. So it's going to send a broadcast now. So what happens here? Since all in the same VLAN, it's one broadcast domain. This particular PC will receive this traffic and it's going to send, hey, this is my MAC address. And it's an unique cast, right? Reply back. It's an unique cast. Now the packets is forwarded based on source MAC and destination MAC. It's one-to-one communication between the PCs here. So the layer 2 multicast is one-to-many. We'll discuss that in the future classes where we use EIGRP and other stuffs. It makes use of this multicast layer 2. So the key components, let me again tell you, the key components are destination MAC, source MAC, and this is a 6-byte header value, 6-byte. So if you look at the Ethernet header, it is 14 bytes, and out of which we have to look at these 3 values. So this is ether type. And this is 2 bytes. The frame check sequence, as I told, that's tucked inside the layer 2, but Wireshark has no insight about CRC, frame check sequence. So here comes your actual payload. So this particular ether type decides what is my next traffic. So based on the ether type values. Yeah, this is a quick overview about layer 2 header. I'll share all this document for reference, and this is about the layer 2 header we have, and let's see how it looks in the Wireshark. So let me open up this capture. If I pick any one packet, if this is an ICMP packet here, and if I go inside the layer 2 header, so what are the values I should see here? So let me take this as an IPv6 address. So let's take a normal packet. So here you can see this is a MAC address. This is my source MAC. This is my destination MAC. And this is what I'm talking about. This is an ether type. So it says it's IPv4. So my next communication is IPv4. So what's next? It's an IPv4. So the three key components, it's again a 6-byte value. This is a 6-byte and this is 2 bytes. So total 14 bytes. Layer 2 header. So as I told you, there is no way we can check the frame check sequence here. That's tucked inside, but Wireshark has no clue about the frame check sequence. You have to see that inside the interface statistics. And if you see, this is a one-to-one communication here. It's from a source to destination. It's a one-to-one communication. If I do something ARP, it's going to filter my packets here. So I got about 560 ARP packets. So let's take this. Let me drill down. I'm looking for a specific packet here. No, let me open up one more capture. So if you look at this, this is a broadcast, layer 2 broadcast. We are talking about the layer 2 broadcast. So if you look at this value, this is my source and my destination all F. This is my source. This is all broadcast. If you look at this, this is a one-to-one communication. This is an unicast. And this is a broadcast. You can compare this value here. This is an unicast. Source MAC, destination MAC. And what is the ether type here? This is 0x0806 is for ARP. So the key component, 6 bytes, and this is 2 bytes, total 14 bytes. Layer 2 header. And if you see, this is an ARP reply. I got an ARP reply, and this is an unicast. If you see, this is my sender MAC address. This is my sender IP address. And this is my target IP address here. So we filtered the packet only with ARP. So this is all the key component we should know about, layer 2 headers. So only then we can troubleshoot. So for my ARP request, if I'm not getting an ARP reply back, then you can figure out where the problem is. So I'm not getting an ARP reply back. So what's the problem? My packet is not forwarded. Somewhere it got stuck in the middle. So with the capture, we get to know about that. So this is about the layer 2 header. And this is how you can see the values in Wireshark. So if you look at this, this is an ARP request. And inside the ARP request, if we look at the ARP packets, as I told you, this is a protocol. The next protocol type is IPv4 communications happening here. This is the ether type, ARP. And if you look at this destination MAC addresses, all zeros, because I don't know who is the destination. So ARP request is a broadcast. And ARP reply is a unicast. For my ARP request, I'll get an ARP reply. This is an unicast. This is a broadcast. There's a key thing we should know about. And my layer 2 header will know about what is next. So what's going to happen next? It's my ARP request. So that's it about layer 2 header values and where we can check that in Wireshark. In the lab, we'll see how we can generate the traffic, and we will, how this Wireshark is trying to sniff those packets, and it's displaying us the same to us. So we discussed about what is unicast, multicast, and broadcast, and ARP in layer 2. And we discussed about layer 2 header types. So what's next? So now we'll see what is layer 3. Let me open up my OneNote here. So in the OSA reference model, the layer 3 comes the third layer, right? This is your layer 3. IP packets. When we talk about layer 2, it's all frames. And layer 3 is packets. So inside the frames, we know what is MTU now, what is source MAC, destination MAC, and ether type. The key thing we should understand. So now let's jump into layer 3. So what are the key components of layer 3? But before that, what is the header size of layer 3? It's a 20 bytes. It's a 20 byte value. And let's see the key components of layer 3. So we call this as a network layer. So how the packet format looks. So it has its own checksum. So we'll see that in the Wireshark. But what are the values here? So the first key thing is about the IP version. We know we got two IP versions, one is IPv4 and one is IPv6. And this is 32-bit addressing we are familiar with. So this is a version, and this is a source, and this is destination IP address. And when we talk about IPv4, that is 32-bit addressing. So this is source IP and destination IP. This is your actual data. This is your payload. And it has its own checksum. If something is changed in the middle, example, if from source to destination, if I send a packet and somebody is trying to do something else, if this is decapsulated and this is manipulated, this checksum value will be in an error. If the validation fails, it's not going to process this particular IP packet. So another important field we discussed about TTL yesterday, and the different types of TTL is 128, 255, and 64. This is used by Linux. This is by Cisco appliances, and there might be, if this is a Linux-based appliances with other vendors, then it's going to use the same TTL. TTL is completely based on the operating system. The source is going to set the TTL. And for Windows, it's 128. You can always check your TTL. Just do a ping is the very best utility to check your TTL. Example, if I do 888, so definitely this is 128 because I get a TTL value of 116. So in the same way, you can check for your Linux boxes and Linux appliances. So we are discussing about this checksum, and TTL is time to leave. Why we need a time to leave? Example, if a source is sending a packet, with a TTL value of, example, if a TTL value of 3, and if I got only 3 routers in the middle, if it is connected something like this, if my TTL value is 3, after the 3 hop, for every hop, the TTL value will be decremented. By 1. For every hop, your TTL value will be decremented by 1. That's the thumb rule. So, example, if I am sending a packet with TTL value of 1, it's going to go here for the first hop, and it will make the TTL value of 2, and it'll send this back to this PC. So now again, this particular packet will be forwarded with TTL of 2, 1, 2, and it'll send back again. So once this TTL value, if it becomes 3 minus 3 equal to 0, so now it cannot forward this packet. That is something time to leave. So how long this packet will be active or alive in a network. So without TTL, what happens? What is the ideology of TTL? If there is no TTL, example, if the TTL value is 255, it means that you cannot go beyond 255 hops. But at 64, you cannot go beyond 64 hops. Example, if you do a trace route, you will get a picture of, the maximum hops allowed is 14. I'm using a delimiter. It's going to delimit all my DNS. Sorry, this is tracer T command. Trace route is for Cisco devices. So now my trace route is happening. So my first hop is my modem. So my IP is 192.168. It's in the 192.168 segment. And here they are blocking this ICMP. And Windows is using ICMP protocol. So for every trace route, 81st, for Cisco devices, it uses UDP. For some appliances, it uses TCP. So how my destination will know every time that, okay, this packet is not making to the destination. So very first time this particular, we have a separate class for TTL, but I'm just giving you a glimpse about TTL, how it worked here. So the maximum hop is 30 here, right? So now this is how my TTL is decrementing when I do a ping. From 128, it is keep decrementing for every hop. Every hop it is decrementing. So example, if there is a routing loop and if there is no TTL value, the packet will be keep running around, right? Because it doesn't have any TTL value. It means that it can go infinity hops. There is no limitation for a specific packet. So that's the ideology behind TTL. And you know what? In the layer 2, there is a loop. And it's very hard to find, and that is called a broadcast ROM, because layer 2 doesn't have anything like TTL. If you look at the layer 2 header, you do not have anything like TTL value in layer 2 header. If I go back to my layer 2, there is nothing like TTL. But if I come back to my layer 3, I got a TTL value here. So it prevents the routing loop. Every time an IP packet passes through a router, the TTL time to leave field is decremented by 1. Once it hits 0, the router will drop the packet and send an ICMP exceeded message to the sender. So in every hop here, if we go back here, if for every hop, the TTL is decremented by 1. So we have a separate class, as I told you, for TTL. For now, the TTL value is decremented here. When we do a ping, we know about that. So this is the 3 key values we should know. This is a minimum value, and this is an average time taken to reach the destination. This is the maximum time taken. This is the minimum time taken, and this is the average value. This is very important when you do a troubleshooting. So when look at this, for one hop, it is my router, it is just taking 1 millisecond. For the next hop, it is taking in average 2 milliseconds. And here in an average, it is taking 74 milliseconds. Here they are blocking the ICMP. And Windows PC, it uses an ICMP to reach the destination. Let me do a ping and I'll show you how this ICMP works together with this trace route. Let me open up my Wireshark. So I'm going to quit. Open up the Wireshark. I'm going to capture my Wi-Fi traffic. So if I do a trace route, simultaneously, if I open my Wireshark here, if I put ICMP, let me put IP dot address equals 8.8.8.8. This is all predefined rules, the color codes the Wireshark uses to distinguish the traffic. Okay, so if you look at here, this is my first packet. It's going to the gateway, this 192.168.0.1 from my source here. This is my source. And this is the destination. and it is using ICMP. So traceroute uses ICMP in Windows. As I told, it differs. And this particular router, right? It's replying back to my source. And what it says, the TTL value exceeded. It's using ICMP. So yeah, as I told you, we have a separate class for TTL. So for every hop, you see this time to leave exceeded. So it will come back to the source. And if you see every time the source is doing again and again, my source is sending a packet back to the destination for all my TTL. If I give an IP address 10.232.0.1, so this particular packet 10.0. This particular destination, it says, hey, your TTL exceeded. I am going to send this back to your destination. This is your source PC. This is how it finds every destination. So it puts a TTL and so first value, it's put a TTL value 1 and it sends to google.com, but it reaches here, my 192.168.0.1 from my PC, that is .104 with TTL of 1. It's going to decrement the value of TTL of 1 minus 1 is 0, and it will send back again to my source, .104. Now it says, okay, I cannot reach this with TTL value of 1. I'm going to increase this. This is by design by the traceroute works. So it's going to put the TTL value of 2, and it's going to send to the same destination, and it's going to reach the first hop and the second hop. Once it reaches the second hop, now my TTL becomes 1 when it reaches here, because it sends with 2. The first hop decremented by 1, and the second hop again it decrement the value by 1, and it becomes 0 and send it back to my PC. The same process happens until here. So for every time it fails, time to leave exceeded, it's going to increase the TTL value. So here the TTL value is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it would the final TTL value from this particular PC, if it sends with TTL of 11, so it becomes in the 11th hop, it becomes 0, and I'll get to know about the destination till I reach. This is how the traceroute works. So if you calculate that, somebody asked a question yesterday, it's a 12 hop away. So there's a maximum hop of 30. So this is how the TTL works here. So this, you can practice this and you will get to know how exactly the TTL works. And in the lab, we'll do this TTL in the future class. So this is all about the layer 3 headers. So the other values we'll be looking at, we'll discuss more, but the main key components, source IP, destination IP, source IP, destination IP, and what is the IP version we are using, and what is protocol ID is something that's related to what is my next protocol. Is it a TCP or UDP? So all about the protocol numbers we see there. And differentiated services is about QoS. This is applicable for both layer 2 and layer 3. We'll see that in the labs in the upcoming classes. But here the differentiated services we see there. What is differentiated services? And we'll discuss about IP identification. So I'll show the Wireshark, that would be easier for you to follow. When I open a Wireshark here, so let's take IP packet. Let me take this IP packet. As I told you, we use checksum, right? Here, if you see this checksum, it uses a checksum status. So checksum says it's correct and it's good. And we got this TTL value here. Time to leave. The protocol, what we are using is a ping. We are doing a ping in ICMP, and the protocol number is 1. And you got your checksum field, your protocol, your TTL. And IP flags, we'll discuss about that. IP flags, we got 2 values. One is fragmentation. That is something I told you, if you're sending your jumbo frames, then this particular packet will be showing up how many packets it's been fragmented. We'll show that. I'll show you that in the lab, how we'll do this fragmentation. If you see here, we done the fragmentation and we saw the fragmentation is increasing on the switch. So it fragmented 10 packets are fragmented here, because I'm sending a packet with a payload of 1600, it has to be 1500. This is fragmentation. And if you capture this particular packet, and you will actually see the fragmented data that's showing up here. The lab will look into it, but just want to show you what is fragmentation field set. The IP identification is the key thing. IP identification is, say, for example, if I open this Wireshark capture, you'll understand better. If I give an ICMP here, this is something I would say, IP identification is stamping your packet. Every packet, you're stamping something like, hey, I am giving you a number, something like 3761. This is one particular conversation. If I send one ICMP request, so there are 4 ICMP requests by default. So for every ICMP request, I'll distinguish every ICMP request with the identification number. It is IP identification number. So example, if I take the IP address, let me filter out the value. IP dot address equals 20001. If I do this, if I drag, I have added this identification number here. We do right click, apply as a column, you will get this field right away here. If you look at this, this is my first ICMP request. For this ICMP request, I get a reply. And if you see, this identification number remains the same. Okay, it's for this is the first ICMP request. This is definitely not possible without the identification. So we never use this identification. If you remove this identification, how it looks. Remove this column. I don't know anything about that. It's just, I can see this is an ICMP. No more information about that. But if I make this as a column, there exactly I see this is first ICMP request, and this is my second ICMP request. Why I cannot track this? If you see, this is the first ICMP request, and this is my second ICMP request, third, fourth, and it is a random number that's generated by the PC. This is a quick identification. If I do a continuous ping to the destination, where I can find, okay, where exactly my ICMP is dropping, which particular ICMP packet is dropped, right? Otherwise, we have no clue. Somewhere it is dropped, but where exactly it dropped. So that gives you more insights about this ICMP with this IP identification. That's very helpful for when you do a troubleshooting. So this is one common, the simple script. I'll give you the script. This is if you do a continuous ping with 5,000 packets, it keeps running. And if you capture the same thing here, it's going to show you where exactly I'm dropping the packets. So if I do ICMP, if I do IP dot address for the Google DNS, so it's keep running, right? So if I stop this particular capture, so there exactly my ping dropped. And with this identification number, you can go through that. You don't want to look at this hexadecimal value. You can always key in about only this. If you look at this particular source, 70.14.243.242, if you compare the identification number, this is for every TTL exceed, you see a different identification number. So it means that this is an every individual ICMP request. So you can find out, okay, where exactly my packet dropped. So this particular script, it will give you a value along with your date and time, exactly where exactly you're dropping your packet. You can run this in the Windows PowerShell, and simultaneously with Wireshark, it will give you more insight about where exactly the problem is and when exactly it happened. This might be very helpful when you do a troubleshooting with a server, and if you're dropping a packet in a particular server, then you can track with IP identification. So for now, let me pause the record. So if you actually see this capture, that's my capture. It says room response seen.
Yep.
Warning is it exceeded the MTU. If you want to check the default MTU for my Windows, this is a command where you can check.
Yep.
And this is maximum is 1,500 bytes. And now I'm sending a packet with the length of 1,600, and it's dropping the packet I cannot make reach to the destination.
Okay.
Just one question. You were showing that ping to that global DNS, right? 8.8.8.
That's right. Yeah.
You are saying like 116. That is a value you have seen for the TTL, right? Actually, that is the TTL for the destination server, right?
No, you got it. What is TTL? I mean, we discussed about TTL, right? How TTL works. TTL is always decremented on every hop.
Yeah, I got that point. Because when you're talking, yeah, go ahead. Please.
Yeah, what's your name, please?
Shine.
Sorry?
Shine.
Shine.
Yes.
Okay.
When you are talking about ping, there will be echo request and echo reply will be there. Okay, yeah. We have sent the echo request. During the echo request only, we are making that TTL to 128, right?
That is using ICMP. It is using ICMP. The traceroute uses the mechanism of decrementing TTL. So TTL, generally what happens, even if you do a ping or traceroute, both use the same ICMP. So for every hop, the TTL will be decremented. Example, if this is a Windows PC, right? This is a Windows PC. So if I do a ping to 8.8.8, so what happens in the background? So here, it uses ICMP protocol. So I'm going to send an ICMP request. So inside the ICMP request, my TTL value will be 128.
That is right. Yes.
Right. Once I reach to the next hop, so it becomes TTL It will check, okay, it is 128 and I'll make it as 127 and send it back to you. Sorry, this is for a trace route. So it becomes 127 and then it goes with the TTL value of 127 from this hop to the next hop. So now my TTL value become 126 in the same way until I reach my destination. Example, in the TTL value is 117 and now I reached. So if you subtract the actual value of 128 and 117, what is the remaining value you get? Example, something like 10.
That is for
a
the echo
number
request,
10.
right?
Don't confuse about that. So for every hop, the TTL will be decremented. That's not for ICMP request and reply. You got it what I'm saying? ICMP, it uses 4 packets, 4 consecutive packets, 4 probe packets. That is for 4 ICMP requests. For my 4 ICMP requests, I should receive 4 ICMP reply. That's it. TTL is the number of hop it takes. ICMP and TTL both are not related. But since we do a ping and it uses an ICMP and it sends a packet with TTL, you got it. You don't mix up with both. ICMP is different. TTL is different. TTL decides your number of hops. ICMP decides, is it for your ping request, I'm getting a ping reply back. ICMP is different. TTL is different.
So if we are doing a ping within this TTL, if we are not reaching the destination server, we will get a message, right?
Yeah, that is a one-to-one communication, right? Yeah, definitely. Yeah.
And can you explain about that trace route, the decremental behavior of the TTL?
No, yeah, we have a separate class for it. So I'll go with every single hop and how this TTL exceeded message happens, because for Windows PC
Both
it uses
with
ICMP.
ping as well as trace route, there is a class.
For a ping and trace route, for ping, that's basic, but trace route, we have a class, and if needed, yeah, we will have a session for ICMP also, no problem.
Okay, thank you.
No problem.
So Arjun sir, what is the difference between the MTU and MSS that you were telling earlier?
MTU is a layer 2. Okay, MTU is a layer 2 where
payload. Yeah,
payload. 1 minute.
1500 bytes. So what is the MSS? Is it layer 4?
It's a layer 4. That's right. Maximum segment size. Yes.
So both of them are relevant. Both of them are relevant.
No, both are not. No, both are not relevant. Both are different. That is layer 4, and this is layer 2.
I have a question which is not related to this class. Where is duplex and all coming in the OSI layer?
Duplex is more with your layer 1, right?
Layer 1 only, yes.
Half duplex, full duplex, yeah.
Okay.
One-way communication and two-way.
Arjun, won't MTU will come under layer 3?
No. MTU comes only with
There is also an IP MTU, right?
The packet, right?
We can set the MTU on the interface and also on the globally, right?
No, that is actually a payload when I set it this, but that not applied to, see, that is the amount of data what that the particular frame that's carrying, that decides your MTU.
Arjun, just
IP packet is different. Yeah,
still I'm not clear, because TTL I understand, I totally understand, it will decrement hop by hop, that part I got it. But when it is coming to ICMP, okay, as I still already told, it will be having echo request and echo reply. Okay, I'm the client. Okay, I'll be sending the echo request. At the end of it, it's a ICMP connection, right? So when I'm sending the echo request, if I'm Windows machine, hopefully I believe it is 128, we will make the TTL value to 128, and it will reduce every hop. It will reach the destination. For example, it is 11 hops away, it will be 170. Okay, now the echo request has reached the server. The server has to send the echo reply back. Okay, while it is trying to generate the packet, okay, it won't take that TTL, right? It will generate the TTL with his operating system, and it will send back to me.
okay.
Okay, because while I'm checking the capture, because see, TTL I understand, as I already told, but this packet, while I'm doing the capture for the echo request and echo reply, I could see I could see the difference, because I'm sending 128. I could, for the echo request and echo reply, I could see 2 different TTL. Usually it should be the case, but you were saying like, there is no TTL coming to the picture. That's why I was getting confused.
No, TTL is purely decided by the source. What is the capture you're talking about? Let me see. What is the capture? You have confusion? Let me see.
Yeah. Sure.
What is the capture you're talking about, please?
So I think that's a capture on my end. I think how
Okay.
can this one?
I think
1 minute. Yeah. What is the, I mean, what is your name? Sorry. Was
Shine.
talking to
Shine.
Shine. See, this is, say, TTL, you get 2 TTL values. See,
Mhm.
I'll tell you. So this is source. This is destination. This is a Linux. This is Windows.
Mhm.
So I calculate all with TTL value 128. And
Mhm.
you do the calculation with TTL 64.
Mhm.
Right? So for this particular TTL calculation, that happens between, this is a peer-to-peer, right? ICMP is a peer-to-peer. In the trace route, that is different. In the ICMP, it is something, hey, are you active? I'm sending 4 ICMP requests. For the 4 ICMP request, I should get 4 ICMP reply.
Mhm.
So my TTL is decided upon this ICMP and my TTL that's been set in the beginning.
That is right.
So here there is no mismatch about TTL. If, for example, if you go back to the ping, that's pretty straightforward, right? So if I do a ping to 888, so here it says it is the TTL is decrementing because what do you think? This communication between the source and destination, it's a peer-to-peer communication. 8.8 is responding to my PC.
That's right.
This
So,
TTL, one minute. Let me, yeah, I'll finish it. Otherwise, I cannot explain you. See, if we, this is something, this TTL, if you minus this 128 with 116, example, I'm saying. So what is the value you get here?
12.
12. So there is 12 routers in the middle. And then in the 12th hop, I am reaching this destination. That's the meaning of this TTL.
Okay, can I share my screen?
Yeah.
If possible, but let me see. Share. I think host is disabled.
TTL will be calculated only based on the route switch, right?
That is it, based on the number of hops, how many hops I take to reach the destination. That decides the TTL.
So when the client, okay, the source sending a ping request, it will calculate the TTL as per its operating system. And when the destination sending the ICMP echo reply, will there be any TTL for that also generated by the back target?
Yeah, exactly. It will send back, right?
Okay, that also has a TTL, right?
Yeah, that also has TTL. For
Okay.
every host in a network has a TTL.
One more.
To send a packet, yeah. I cannot see.
So, Arjun sir, TTL will decrease only by layer 3 device. I mean gateway only. Or let's suppose any like 2 or 3 switches are also in between the traffic. So,
sorry. What is the question?
let's suppose I am pinging to one of the destination. Okay. So my question is that so TTL is only decreased by gateway, like how many gateways are in between the device, or
that's exactly how many IPs in the middle that does the routing, that actually look at the TTL, and your TTL will be decremented accordingly.
Okay.
Suppose if packet enters a MPLS network, there it won't be decremented, right?
Sorry?
If our packet is going through certain MPLS network, in that case, it won't be decrementing the TTL, right?
I think you have to do some tweaks with MPLS for that.
Okay.
Then, yeah, that will not be. There is some tweaks it has to do with MPLS.
Yes, sir, that you need to do, ignore the MTU. So there is a thing, there is a command in MPLS that you can use. and it ignores the MTU. So when you send the packet and it traverses the ISP MPLS core, then the attacker who is attacking it, he will not know that, okay, how many hops the packet has traversed, and it will save the MPLS core from any attack through flooding or anything like that.
Yeah.
Ji.
And Shine or someone, he asked a question, right? So if you see this, my source is the public IP, and if I see the different TTL, it's because its own TTL. See, it is 64, and 64 minus 45, what is the value? So how it will reach my destination from 64 to 45 is something, how much it is? 14.5, I don't know, with my. So
can you just search for IC?
Example I'm saying, say here, if you reduce something like 14 minus 5, right? So 4, 5, 9.
19.
Yeah, 19. So it takes 19 hops to reach my destination. Example, I'm saying.
Yeah.
So one minute, yeah, let me finish. So this TTL is decrementing based on the source. So
Exactly.
it sent a TTL with 65, and it has to go through these many hops, 19 hops, to reach my destination. And my TTL is, it's showing my TTL is, decrementing, and I have a route to your destination, and this is the number of hops I take to reach your destination. That's the meaning of TTL.
Yes.
And this is purely on layer 3 header.
Exactly. In this case, the TTL is set by that 134.224.140.99 host, correct?
That's exactly.
Now, can we just go back to ICMP packets?
This is ICMP or UDP. And let me open up the ICMP. Yeah.
There is no ICMP. Okay, can you just take one request and reply? Just
ICMP request and reply.
Yeah.
Yeah, this is all request, and I didn't get any reply for it. This particular pack capture. Let me go back to one more capture. This is okay. Both are same. Yeah, both are same. I have to do a capture again. It's my Wireshark. Yeah, tell me. Let's take a capture. Yeah.
Yeah. Now, can you just filter with ICMP?
Okay.
Can you just take one ICMP echo request and reply? You have some filter.
Yeah, this is ICMP request and reply.
Yeah. The first request, we will take two requests. Okay, one is one request and reply. Okay, the request is being initiated from your PC to the Google DNS.
Yes.
Okay, if you look at that TTL, that is 128. Okay, now the return packet, that is reply packet, that is being initiated from the Google DNS, correct?
Yes, that's right.
So the second packet, this field TTL field is set by the DNS, right?
Yeah, it's all ICMP is used here.
Yeah, the TTL value, it is for the echo reply, the TTL value is set by the Google DNS server, right?
That's right. Yes.
It's clear now.
Yeah, that's what I'm saying. See,
Because,
this is
no,
okay.
no,
You can.
Why I asked, while you were just trying to ping from CMD, you are saying the TTL is set by the value we were seeing 116, right? I'm not sure whether it might be by mistake, but you are saying the TTL that 116, it was from the machine. That is what the question, I got confused back, because actually the TTL for the return packet, it is set by the DNS server.
Yeah, whomsoever is replying for ICMP request, it has to reply back. So it has to add its own TTL. That's what I told. Even in the chat, it's decided by the source.
Because I just said, like, it is the client. That is the reason that I got confused.
No, yeah, 116 represents that how many hopes that has reached and getting the reply.
That's right.
Now, I think we have three possibilities here, right? Now, either it can be started from 128 or it can be started from 255, correct?
Yeah, that is by looking at the values, we will get to know, is it 128 or 255? Here, you know, you don't see anything with 255, but if you capture something with Cisco appliances, you would see something like 255 here.
I'm just talking about a 116 because either the packet which might have generated with the TTL value 128 and it has passed 12 hops, so now the value is 116, or else the packet TTL value, it might have started with the 255 and it might have traveled almost 100 plus hops, right?
100 plus is not practically possible in the real network. Maximum it can be 30. Okay. Maximum is 30. Maximum is 30.
Yeah, now it's clear.
Yeah, you don't see something like if you got 64 with TTL 64 and I see a TTL 3 and I got a response back. That's really, the number of hop is too high, but I never seen that in the practical scenarios where I see the TTL maximum. It could be below 30.
Okay.
Sir, one question, sir. Sorry to interrupt you. Sir, ये जो frame था, sir, layer 2 frame, right? Okay. We said that the maximum size can be 1500 bytes. Okay, sir.
What is that frame size? No, I'm talking not about.
So MTU, sir.
Yes, size. Yeah.
So, sir, MTU, we said that it will be on layer 2, right?
Yes.
So layer 2 frame size will be 1500 or 1518 to be very exact, right? So sir, ये जो पैकेट होगा, पैकेट layer 3 पर या layer 4 पर जो segment होगी, sir, इसका भी size, this cannot exceed 1500. Is that correct?
That MTU that sits back only with layer 2. That never goes back to layer 3 or 4.
Ji.
See, when the packet arrives to layer 2 with all this encapsulated payload, that is something like it should not exceed the amount of data. So that's how they have designed. So that's why we are reducing the MSS. If the question is something, the MSS, why we are reducing for GRE is because we are adding that extra header that makes the MTU bigger. So for that, I'm reducing. So the MTU, you can say you are sending a parcel and your parcel limit is something like a 5 kg and you cannot send more than that. So that is the total amount of data that can be carried in the network. That's it. So if you make some changes with your layer 4, so you have to change your maximum segment size, because the segment length, if it exceeds and if it is spoiling the MTU size, and if it is increasing the MTU size, then it is a problem, right?
All right. Okay. So we need to adjust such a way that when the packet, after passing from layer 4 to layer 3 to layer 2, it does not exceed more than 1500 bytes.
Yeah, MTU should not increase. Yes.
Okay. All right. Okay. Thank you.
Hi Arjun, this is Kavi here. Actually, I have a question with regards and the topic what we are seeing. You said like the maximum MTU is 1500. On this, we have IP header of 20 bytes and then a TCP header of 20 bytes. And you said like the data link will be 14 bytes, right? So all this will be reduced. All this will be minused with the 1500, and the remaining only the data will be sent in the packet. Is it correct?
No. What is your question? Can you?
No, the maximum load that packet can take it. Let's exclude the TCP header 20 bytes and the IP header 20 bytes, and you said like the data link frames will be 14 bytes, right? So all this will be reduced. The maximum the data that packet can take is 1500 minus this 3 value. Is it correct?
That's correct. If it is exceeding, your end appliances should fragment the data. If it is coming with a bigger MTUs, it should fragment the data. See, if you have what I'm saying, example, if you got 2 different MTU like this between source and destination, I'll tell you.
Okay.
It is going to terminate the connection. The MTU mismatch should not happen. So if you're sending a packet here, if your MTU is same here, there is some device that is connected here and you have configured this particular port as a server, there you got your jumbo frames. But what if this sends to your appliance in the next hop? So it is going to fragment this data and send it to the next device. So the MTU has to match. So you have to do exact MTU matching that should happen in both end. But this is all the default behavior I'm talking about. This is the default behavior, and you can check in the device. That's how the MTU is configured by default. I'm talking about the general scenario.
Yeah, that is correct. But in terms of data payload, this 54 bytes will be reduced. So the maximum the data is traveled is like 1446. Correct me if I'm wrong.
That's correct. See, if you see this ping, if you do this with 1600, what happens here? For this is length, and if I send something like instead of 1500, if I'm sending 1800, so I cannot reach.
Yeah, you cannot reach, but the maximum the payload will be in the packet is 1440. 46.
1500 is the MTU.
Yeah, 1500 is the MTU, correct. But again, this TCP and IP payload will be added, right?
See, what happens if you look at this OSI model? This in every layer, this particular payload will be encapsulated and pushed back to the lower layers, right? So when it reaches the layer 2, what I'm saying is, if this MTU is somehow your segment is increasing this MTU, and it's going to drop. So here, if I'm sending an IP packet with 1600 bytes, it's not, it's dropping the connection, right? It's not making to 8.8.8 because my MTU on my PC, it's been set to 1500. So that depends. So if you change the MTU and if it can fragment, then you can do it.
So what's happening here is including
one minute. See, this is my Wi-Fi and this is my MTU, and see, this is a number of bytes what I send. And if it is crosses this 1500, it's not happening. If I make it as a length.
Yeah, I understood this point. The maximum it can take is 1500. I understood that, but you draw an diagram. Let's take that and then that let's construct an MTU there. For L2, it will be like 14 bytes will be added. So the maximum MTU is 14 will be minused with the 1500. Correct?
1 minute, you're talking about this MTU, this is 1500. This is a payload. This is a payload. See, this header information is added along with that. If you see the Ethernet type 2 frame, that is 1518 bytes. This 18 bytes is, this is 6 bytes of destination, this 6 bytes of source MAC along with this Ether type 2. So altogether, how much? 12 plus 2, 14. That's added with this 1500 bytes and it's sent. And this checksum 4.
Okay, I understood. But you said 1500 is the maximum. So if you see here,
I'm again saying, see, this is the data payload I'm talking about. So this comes under IP, ARP, etc. It's all this data payload.
If I understand what he meant by on the data payload, it is not complete data. The data has 20 bytes of IP header, 20 bytes of TCP header. So the actual data from top layers, right? It is 1460 plus 20 bytes of TCP, 20 bytes of IP, total 1500, right? So he's saying the original data is 1460. Is it right or wrong? That is what his question is.
What is the original data is what
I mean,
you are saying from
the original ICMP data. I mean, ICMP sends some bytes of data. It can be the original payload can be maximum 1460 bytes. That is what his question was.
The actual payload is 1460. So what you're telling here, so this is what is this?
That's what 1460, the actual payload
plus TCP header 20 bytes and then the IP header 20 bytes. Is it so? The payload I'm talking about, not this one.
No, I'll go through this and I'll get back to you. Your question, can you repeat it one more time? What is the 1460? What is the value you define? 1460?
Yeah, 1460 is the original payload. It contains the data. Because if you say 1500, again when we go for the layer 3, IP header 20 bytes will be added, and again we go for a TCP header, again 20 bytes will be added.
Yeah, altogether is the payload. Yeah, that's right. That's right. Altogether, this is all the header. What you see in the left-hand side, this is the header, and this is the payload. For in every layer, this particular payload will be appended with the header values. So altogether, it should not exceed 1500. It can be your TCP, it can be your ARP, it can be your IP payload. That's it doesn't matter, but it should not exceed 1500 by default. It decided here, this particular PC. And this is something in the recipient who can accept the fragmented packets, you can send again. But here it's not accepting my connection. If I make it as 1600, my packets is dropping. You got it. So this is the public network. We have no information about that. We have a lab where we'll do if we increase the MTU, but still I can ping because my switch is fragmenting here. So it is not static, that because how then we can send the jumbo frame? That is not possible, right? You got it, what I'm saying?
Yep, I got it. But so along with this data payload, 1500, this 14 bytes will be added for the layer 2.
Along with the 1460.
Yeah, along with this data payload is 1500 bytes, right?
Yeah.
Okay, there IP header and TCP header will be added.
Yeah.
Okay, that's I understood. Here, if you see the bottom, you can see like 1518 bytes. No, at the top. Yeah, here. So yeah.
64 to 1518.
1518, yeah.
So you mean to say it can exceed 1500?
Yes.
So Kavi, I want to give you some hints here actually. This is Sridharan here. So if you are sending forget about this, the ICMP ping right now, we are sending about the packet load of 146 and then 20 bytes you are adding, that is a question I understand, right? So if you are sending a 5 gig file or a 5 GB file from A to B, how the packet is going to send from A to B?
Is it a question to me? Yeah. It's like, it will have the data, and then along with this, it will have the TCP header, and then
so
the
it's
IP
going
header.
to packet everything, right?
Yeah,
it's going to packet everything.
Yeah.
So it's going to put the payload, your data inside that. So it's going to fragment everything, it's going to just send 1500 bytes in packet A, and then it's going to keep on sending all the packets from A to B and then finish it. That is exactly he's trying to explain,
yeah, I understood,
your payload.
Sridharan.
Yes,
yeah,
yes,
I understood.
to the pipe. Yes.
Yeah, I understood.
So what is the question here exactly?
My question is, if you see the payload is 1500 bytes. Okay, if you see, in this 1500, 20 bytes of IP header will be added, and then 20 bytes of TCP header will be added. So the actual data, that 5 GB I'm gonna send it is in one packet. Maximum I can able to send is 1460.
Correct, yes, sir. Yes, that's correct.
You're
yes.
right.
Yeah,
You're
that's
right.
correct.
Right. Okay.
Because the
So,
MSS is 40 bytes less than your MTU size. So you take it that way. So if you subtract 40 bytes and it becomes 1460.
Yeah, 1460. I understood now. And then if you see is
no, in real time scenario, I will give you one more hint as well. If you think about this jumbo frames, what he is trying to explain is right. The real time scenario, I have this is a real time thing happening. I have experience in my career actually, right?
Yeah.
So we have a replication, right, between data center A and data center B. Suppose it's in Trumbull and then Virginia. You have 2 data centers, and I have my mainframe data big, in they push a lot of data, replication data from source A to source B. We have a nexus between that, and we have a same network in that. Okay, so we have OTV concept at that time actually, and I'm talking about in 2014 something like that actually, right? We have a OTV connect, we have same network data centers between that, right? Actually, where they couldn't replicate the traffic actually. They are getting the connection timeout. When we checked with the vendor, what exactly happened when we check in the Wireshark at that time? This was real time happened actually. We taken the Wireshark and then say that your source is sending a jumbo frames, which our network is not allowing because the vendor put a dark fiber that's not allowing the data jump of frame. Then we requested a vendor, hey, you have to allow the jump of frames because it's a replication data. If I keep on sending 1500 this thing, it's going to take ever, it's going to take 5 days to complete the replication of 1 day data. So that's where this the payload comes into the picture, jumbo frames, right? Actually, so we set the jumbo frames so they can set maximum limit and then send it across as per the destination and the source agrees. If it has to match, both has to match the same MTU, then they can just send each other actually. So that's where so I'm just giving a real-time picture. That is how the data transmit between that and the jumbo frames and the MTU lies actually.
Yeah, exactly.
So
That's
all
the
that
time
yeah.
I am trying to explain the same thing. This MTU has to match, and if you can send how much data, but it has to fragment. It has to do a
yes.
It is
That's
not
right.
fragmenting.
Yeah, I just we need to take it very simple. This is not something complicated thing actually. So the real time, this is how it occurs actually.
Yeah.
Hello. So in the replication path, okay, all the devices in that path should support jumbo frames, right?
Exactly. That is you have a dark fiber that is like a point-to-point link between the data center. Okay, I'll give you that what is in between actually. A dark fiber, like DRW, that runs between the data center, that is provider given the pipe directly from my nexus to the other side nexus actually. So we have so the nexus supports the jumbo frames actually,
Okay,
right?
both
And
side are
then
directly supporting
Nexus
jumbo
takes the
frames.
jumbo
that's
frames
right.
of 9216. So both
Yes.
side has to match.
Yes, and also the mainframe devices that connected directly to the VPC on this Nexus, right? That supports it. So it's just as long as both side of the mainframe devices are accepting that, it should be fine actually. Even the same applies to the
Okay,
storage
got
as
it,
well
got it.
actually, the replications as well. You connect to the storage switch, the Nexus 5Ks when you have, and then between the data center. So mainly those jumbo frames comes into the picture of the replication of the data actually in the real-time picture. Other than that, you don't touch the MTU on your machines or VMs or anything like that, right?
Yes.
Actually, we don't touch anything like that actually. Okay,
Yeah.
we never get into the picture of doing anything crazy like that actually, because it's going to impact everything, right? You can try that in your PC. You have go to the Ethernet card and then check there is an MTU. You can just adjust that, but it's going to give you an impact actually, right?
Yeah,
Until
that's right.
unless nobody does it, we'll not get into the picture. This happened only with the replication, guys, in the real time actually. This won't affect anything else.
That's correct. Okay. Actually, I am an FI admin. We are the private cloud. We are doing some storage. Okay, storage application.
Okay.
So there
Okay.
we are using jumbo frames 9000. Okay, so it's in the normal scenario we see 5000 1500, but in this kind of big data transfer environment, it's used to see jumbo frames.
Exactly. Until unless you inform your provider to achieve that, if you're an FI admin, so what you're using a GLB or is it an LTM you're trying to use as FI as a load
Yeah, it's an
balancer? Or,
LTM
okay.
hosted on new hardware R15 and 100. It's a
Okay.
5
Okay.
latest hardware. Okay.
Yeah, I used
It's
to manage
usually-
FI also in my environment. We have a lot of
This
FI,
is
so I
a
work with FI.
powerful box actually. It's a newly introduced. It's a R series box. So
Okay.
Sir, once
Can we
again,
proceed
for
to the next
storage
topic?
application.
no, once again, for dark fiber, there is a point-to-point link so that we can able to adjust the MTU size into jumbo packets or something. But if it is goes under the MPLS kind of scenario from data center, from one data center to another data center, there might be challenges in passing.
Exactly. You
Adjusting
cannot.
this,
Yeah, the same scenario happened. If the dark fiber is cut down, right? Actually, they have an issue today also. Even if your OTV can be adjusted, or the VXLAN, what you call the advanced version of this, right? Actually, as long as the IP reachability, you'll have the same network. It can cover this one actually, right? But if you are sending across to the normal MPLS or anything like that, you cannot expect everything should be like, coming through that actually. And now we are moving into a completely different world actually. So like, you have SD-WAN, right, actually. So in that, in that also, like, you have something called like, the topology changes. You can set a VPN, which VPN has to go through